Hello, today's lecture is the pre-lab lecture for our Periodic Properties of Light-Emitting Diodes lab. So in this lab, we're going to be working with electrical circuitry. Okay, so we're going to have a battery that's going to end up powering a LED light bulb, and we're going to be observing the energy associated with that LED light bulb and how that relates to chemistry. So before we get into discussing the specifics of LEDs and of the system that we're working with, we first need to establish a background knowledge on electrical circuitry and conductive materials. So there's a few pieces of terminology that we need to lay down before we can understand what's going on here. So first off, we need to discuss current. So current, which has the symbol given of I, is the speed of electron flow between 2 points. So if we think about a current flowing within a wire, so if you have a wire that's hooked up to a power source, the current is the movement of electrons over that wire. Okay? And so the current, which has units of amps, is actually known as the charge per second. So the movement of this negative charge over a period of time gives the amperage or the current of our electrical flow. The next concept that we need to introduce is voltage. So voltage is the potential energy that causes electron to flow from one point to another. So batteries produce voltage in what's called a DC or direct current voltage. So we know on a battery there's a positive pole and a negative pole. So if we have a wire hooked up to the two different poles of the battery, and we know that current is the movement of electrons through the wire, this voltage difference between our positive and negative poles is the potential energy that forces electrons from the negative pole to the positive pole. So these electrons are moving through that wire as current. Okay? Next term is resistance. So the resistance, first off, so the voltage, another word for voltage is potential. Okay, so voltage and potential, these terms are interchangeable, and the units for this voltage is the volt. All right, our third term is resistance, which has the symbol R, and that has a unit of ohms. And so that resistance determines the current based on the voltage. All right, so based on the voltage. Okay, so the resistance determines the current based on the voltage. So if you have a high resistance, you have a low current. If you have a low resistance, then you have a high current. So every material that is used to make up an electrical circuitry has a built-in resistance in it. So metals, which are highly electrically conductive, have a low resistance, therefore they can have a high current flow through them. Whereas plastics and resistive materials have very high resistance, therefore they can have very low current. And so there's an equation called Ohm's law, which is shown here, V equals to IR, that is Ohm's law. Ohm's law is a simple equation that relates voltage, current, and resistance to each other. So we can see here that as we have a higher resistance, you're going to have a lower current. If you have a lower resistance, then you have a higher current. So that correlation is very clearly displayed here in Ohm's law. And if we take a look at the relationship between voltage and current in highly conductive materials, so here we're talking about, for example, metals, highly conductive materials, we can see the relationship between voltage and current is linear. And the slope of that linear current is going to be equal to R resistance. So what this means is that even at very, very low voltages, you still produce current. So electrons can flow even at very low currents for highly conductive materials such as metals. Okay, so now that we've introduced electrical circuitry in conductive materials, let's start to talk about light-emitting diodes that we're going to be using in lab this week. So light-emitting diodes are a circuitry element called a diode. So a diode is defined as a semiconductor circuitry element in which current can only flow in a single direction. So there's a high resistance in one direction, which means that the current cannot flow through that direction, and a low resistance in the other direction, meaning that current can flow. Okay, and for a light emitting diode, that's going to be a diode circuitry that lights up an individual light. And we're going to be focusing today's lecture in this lab on identifying what different wavelengths of light are each of these light emitting diodes going to produce and why. All right, so if we see the structure of this light emitting diode, we can see again we have two different poles that would hook up to a positive and a negative side of a battery. Okay, and so being a diode, the current will only be allowed to flow in one direction. Okay, so which means if you hook up the positive and negative side of the battery, you're going to observe the current will flow in one direction, but if you switch the poles to the other direction, the current would not flow. Okay, so that's what a diode means. So we introduced this idea of a semiconductor here in the definition for diode. So what is a semiconductor? So a semiconductor is a material with an electrical conductivity that falls somewhere between a conductor and an insulator. So again, a conductor is something that conducts energy easily. An insulator is a material that does not conduct electricity. So a semiconductor is somewhere between the two. And so these semiconductors typically consist of crystalline structures of semimetals. So for example, here we can see this crystalline structure. So we can picture this as being a cube crystal that is composed of various different semimetals. And so if we look at our periodic table, the zigzag line on the right-hand side of the table is going to show up our individual semimetals. Okay, so we have our metalloids, our semimetals, our boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. Okay, so these semiconductors are typically made of crystalline structures of these semimetals. And so the way that our conductivity works in a semiconductor is that electrons must move from one element to the other within this crystal. Okay, so you'll have some of your elements that are going to be more conductive and some that are going to be less conductive. In order for current to flow, you need to have electrons moving between these individual currents along the crystal in order to conduct electricity. Okay? And so for a semiconductor to work, you need to have a sufficient voltage that is above what's called a threshold voltage in order to conduct electricity. And so what that threshold voltage means is that your voltage needs to be above a certain amount in order to conduct electricity. So any voltage below a certain threshold voltage for your semiconductor is not going to conduct electricity. So if we take a look at the current versus voltage plot for a semiconductor, we can see that it is not a linear plot. Whereas on the last slide, we saw that it was a totally linear plot for conductive materials. For semiconductors, we can see that there is no current that flows until we pass a threshold voltage. So underneath that threshold, no current flows. Once we pass the threshold voltage, we can see that current can then pass. Okay, so at very low currents, semiconductors do not conduct. At very low voltages, semiconductors do not conduct electricity. At high voltages, semiconductors do conduct electricity. And eventually you'll reach a point where you've plateaued your amount of current that you're going to reach. And so if you apply more voltage, you are not going to get any increased effects for your current. So why is this behavior observed in semiconductors, and why is this behavior different between conductors and semiconductors? So in order for current to flow through a material, electrons must pass between what's called a valence band and a conductance band. Okay? And so electrons need to flow between our empty and filled valence and conductive bands. And so there needs to be enough energy for these electrons to move in between these bands in order for electricity to flow. And so if we take a look at metals, if we look at the relative amount of energy between our valence and conductive bands, we can see that these energy levels of the two bands actually overlap with each other. So at any potential or any voltage or amount of energy applied, we can see current flow at any voltage. For our conductive materials, because this energy for our valence and conductive bands overlap. Whereas for semiconductors, we can see the difference between our valence and conductive bands. There's a small energy gap that we call a band gap, which is the energy difference between our valence and conductive bands. So this is a very small gap for semiconductors. Whereas for insulators, we can see that this band gap is very large. So we can see, so typically when we talk about energies, we talk about energies in units of joules. But there's actually another unit that we can use to describe energy, which is the electron volt. So 1 joule is equal to 6.242 times 10 to the 18 electron volts. So we can talk about these energy difference in units of small amounts of electron volts or large amounts of electron volts. Okay? And so that electron volt energy, that relates directly to the voltage applied with a battery. Okay? So these band gap energies relate to the amount of battery energy that you need to apply to a circuit. So to overcome this small band gap, you need a small amount of external voltage. Small external voltage. To overcome this small band gap in order to have electrons travel between our valence and conductive bands. Whereas for insulators, you would need a large amount of external voltage in order to have electrons move in between these different energy gaps. So if you talk about an ultimate insulator such as plastic, the amount of voltage you would have to apply for plastic in order for that to conduct electricity, the material would catch on fire first before it's actually able to conduct electricity. So for insulators, that gap is just way too large. But for semiconductors, it's a small gap that's manageable to get over. That small gap is your threshold voltage. Okay, so what happens when electrons cross an energy gap? So based on our lecture material, we observe that when you have electrons that are promoted to high energy levels, when those electrons cross an energy gap, they have to release that energy in the form of electromagnetic radiation, or light, equals to h nu. So Planck's postulate here, E equals to h nu, talks about the energy of light corresponding to the frequency, or the energy of light corresponding to the wavelength. So the light that gets emitted as electrons cross an energy gap indicates the amount of energy of that individual gap. Okay? So when we're talking about crossing an energy gap for a semiconductor, we have this band gap energy in electron volts. And we have that energy, that band gap energy relates to the elemental composition of the crystal. So depending on which one of the individual semi-metal materials make up that crystal, it determines the amount of energy that makes up that band gap. And so that energy gap size tells us what wavelength of light comes out. So therefore, the wavelength of light produced by an LED relates directly to the elemental composition of the crystal. So our individual lights that we observe for an LED, whether it's a blue light, a red light, a green light, a yellow light, whichever type of light, it depends on the elemental composition of the crystal, because each of those elemental compositions have their own unique band gap energy. So let's delve into this in a little more detail. So how does the elemental makeup of a semiconductor crystal relate to the band gap energy? Okay, so in order for this electricity to flow, electrons must be removed from the outermost valence shell and be transferred between atoms in the crystal. So remember, our electrons have to move through that crystal in order for their electricity to flow. And so there has to be enough threshold voltage in order to cause that current to flow. So you need to have a strong enough battery to light this crystal in order for those electrons to move. Okay, so the valence electrons that are in this crystal are also used to form the crystal lattice. So the individual bonds that hold the crystal together are also being formed by these valence electrons. So remember, valence electrons, those are electrons in our outermost energy level. So I ask you two questions. The first question, is it easier to remove electrons from a larger atom or from a smaller atom? And the second question, what makes a stronger crystal lattice? Small atoms or larger atoms? Okay, so in order for us to consider the ease of these electrons being able to move, we need to discuss how easy is it to loosen these electrons so that they can move through the crystal. So we have to think about how tightly they're being held. So let's consider first our question one. Is it easier to remove electrons from larger atoms or smaller atoms? Okay, so if we think about how electrons are being held into an atom. So we have our positively charged nucleus, and then we have these negatively charged electrons. And so these electrons are being held into the nucleus by electrostatic interactions. So a positive and a negative, you can think of these as magnets holding them in together. So the question is, for smaller atoms or larger atoms, which one is holding these valence electrons stronger? So for this, in order to think about this, I ask you to think about holding two magnets close to each other. So if you have a positive and a negative side of a magnet, okay, so here I can actually draw this. So if we have a positive side of a magnet and a negative side of a magnet, so if you have them separated by this distance, consider it or compare to separated by this distance. Which one is going to feel a stronger attraction to each other? Obviously, the magnets that are closer together are going to feel a stronger attraction. The magnets that are further apart are going to observe a weaker attraction. So let's consider this now to the size of these atoms. For small atoms, your valence electrons are much closer to the nucleus. So it's like this condition 1 when our magnets are very close to each other. Whereas for larger atoms, our valence electrons are far away from the nucleus. So it's more like our condition 2 with our magnets. So if we go back to our question here, question number 1, is it easier to remove electrons from larger or smaller atoms? We can see that the electrons are being more tightly held by smaller atoms and more weakly held by larger atoms. Therefore, it would be a lot easier to knock off the weaker held electrons on our larger atom. So it's easier to remove electrons from larger atoms. Let's think about our question 2. What makes a stronger crystal lattice? Smaller or larger atoms? So the energy that holds together a crystal lattice, what's called a lattice energy, is proportional to 1 over the interatomic distance. So what the interatomic distance means, it talks about the distance between the individual atoms within the lattice. So there's an inverse relationship. So the larger the interatomic distance, the less the lattice energy. So the less tightly that lattice is being held together. The smaller the interatomic distance, the larger the lattice energy. So therefore, the stronger this lattice is being held together. So if we consider the packing of large atoms versus small atoms, if we have a lot of very small atoms that are being packed into a crystal lattice, our interatomic distance is going to be very small. Therefore, our lattice energy, the energy holding all these guys together, is going to be very high. Whereas if we have larger atoms that make up a crystal lattice, we can see that the interatomic distance, so the distance between the nuclei of neighboring atoms, is instead going to be very large. Therefore, our lattice energy is going to be very small. So in order, if we think about electricity moving from electrons being freed from the lattice and being able to move through the solution, we have a weaker held valence electrons for larger atoms, and we have a weaker held crystal for larger atoms. So therefore, the larger the atoms are, the further apart these atoms are held in our crystal, the easier it's going to be to flow electricity. Okay? So basically, we can state here that the size of the semi-metal materials, semi-metal atoms that make the crystal lattice determine the band gap. Okay? So the larger your atoms are going to be, the easier it is for electrons to move. Therefore, the less voltage is required to move those electrons. Okay? The smaller your atoms are, the more tightly those valence electrons are held in, the more tightly the lattice is held together. Therefore, the harder it is to move electrons through the solution, therefore the larger the band gap energy. Okay, so this slide here kind of summarizes that conclusion that we pulled out. Smaller atoms in the crystal, more energy needed to remove electrons, stronger lattice energy, higher band gap energy. Therefore, if we consider the light that comes out, the higher the band gap energy, the higher energy light, therefore the lower the wavelength. Because remember, E is equal to hc over lambda. The higher the energy, the lower the wavelength. If we have larger atoms, less energy is needed to remove electrons because we have a weaker lattice energy. Therefore, we have a lower band gap energy, lower energy light, therefore higher wavelength light. All right? The lower our energy, the higher the wavelength. Okay? So we can use this concept in order to discuss the individual wavelengths of our LED lights based on their elemental makeup as it relates to the size of the individual semi-metal atoms that make up our crystal lattice. So the last thing that I want to speak about quickly in this lecture video is the temperature dependence of semiconductors. So temperature affects semiconductors uniquely. So we observe that if we're looking at conductors, we see as the temperature goes up for conductive materials, so remember this is like true metals, we can see the resistivity of the material goes up. Okay, so it is resisting current flow as you get to higher temperatures. Whereas for semiconductors, like our LEDs, we observe that as we increase our temperature, the resistivity goes down. All right, therefore our current is going to go up as our temperature increases. So this is a really unique trend that is observed for semiconductors. This is a totally opposite trend between conductors and semiconductors. So why is this trend observed? So let's think about what's happening. Increasing temperature increases the molecular vibration in the crystal lattice, which means that each of these individual atoms within our crystal lattice start to vibrate. So they're moving back and forth, vibrating around. Okay? And so the effect of vibration in this crystal lattice has the effect of pushing all of these atoms a little further apart. And so this has the effect of increasing the interatomic distance. And so by increasing our interatomic distance, we're decreasing our lattice energy. And when we have a decreased lattice energy, that means we have a lower band gap energy. Okay, so decreased lattice energy, it's easier to kick those electrons free. So we have a lower band gap energy, lower band gap threshold, lower energy of light, therefore the higher wavelength of light. Okay, so we can see that the individual wavelength of light put out by an LED is dependent on the temperature in which this LED operates. All right, so that's it for the background material. Make sure that you read your lab manual and then complete the pre-lab quiz. Thank you for your time.